Thank you. Not often do we ponder as we drink our coffee in the morning to ask what caffeine really is. Even rarer do we question what our world would look like today if coffee had been discovered sooner or not at all. Another question that we may not ask, or shall we, is what may vitamin C, pepper, house cleaning, and salt have in common? Apart from being prominently featured in Le Couture and Bourson's Napoleon's Buttons, How 17 Molecules Changed History, these molecules and their utility have been discovered serendipitously. Another question we don't often concern ourselves with is how long it takes to boil an egg. How clean is the water? What's the egg size? What's the initial temperature of the water or the egg? What altitude are we doing this experiment at? Yes, boiling an egg could be an experiment. This was one example in Science of Cooking, a book by a physicist and professor of molecular gastronomy, Peter Barham. These books and my commencement lecture in Romania, where I went to undergrad, this is a half funny, half serious lecture given by a professor in the department. That lecture geared my passion for cooking towards cooking science. The lecture was about whether Tom or Jerry's coffee cooled faster if Tom added milk to his coffee right away, while Jerry took a telephone call before adding milk to his morning eye-opener. As a first-year grad student, I heard talks by professors in the department working hard to captivate us and attract us to work in the most exciting, rewarding field, theirs. And one such talk started simply with the statement, I like to cook. I like to cook, and the periodic table is my pantry. Over the 20th century, mixing chemicals has progressed from mere experimentation to design and synthesis of materials with targeted properties. It is a propitious coincidence that I get to speak on the day of the 2013 Nobel Physics Prize announcement. Today, François Englert and Peter Higgs were recognized for the discovery of a mechanism that proves that particles have, or that shows why particles have mass. The particles they predicted to exist nearly 50 years ago was confirmed last year by experiments at the Large Hadron Collider, and I have to give a shout out to my Rice colleagues who lead some of those experiments. But even the first Nobel in physics in 1901, which recognized Röntgen for the discovery of X-rays, at the time was just a new and exciting find with unforeseen applications and perils. My research is centered on design and synthesis of novel materials. The goal is twofold. On one hand, this is intended to explain material properties that, for example, make the transistor the fundamental component of modern electronics, or to inform the design of functional materials, like, for example, those for magnetic data storage, which have afforded the miniaturization of our cell phones, computers, digital cameras, etc. On another hand, cooking with metals, or with any chemicals for that matter, renders the design more predictable and controllable. The two examples that I mentioned, both were recognized with physics Nobel Prizes. One in 1956 for the discovery of the transistor effect was shared by the discoverers Bardeen and Brattain and their boss, Shockley, who had actually discouraged them from working on this experiment. The second is a recent recognition from 2007 of the 1988 giant magnetoresistance effect discovered simultaneously by Albert Fert and Peter Grunberg. People designing materials like me are looking for potential candidate compounds and suitable experimental techniques to produce the new systems that will address one specific problem like the magnetic storage or thermoelectric materials. We already saw what a successful story looks like, a trip to Stockholm in December. But the failure scenario is often just as rewarding. An example comes from the recent history of the iron-based high-temperature superconductors. A Japanese material scientist, Hideo Hosono, was well known for his work on transparent semiconductors. He thought of a mixture of three elements, lanthanum, iron, and arsenic, as a potential good candidate for such a new semiconductor. Hosono chose tin, a low-melting metal, as a solvent for the three elements to form the compound that interested him, overlooking the fact that tin often sucks in oxygen if available and loans it to the liquid mixture when hot. And this is how he ended up with a material with all four elements, lanthanum, iron, arsenic, and oxygen, now an archetype for the so-called iron nictide superconductors. The beauty of this discovery is enhanced when considering not just the new physics these materials have unveiled, but the fact that they get us now closer to understanding a 25-year-old mystery, which is that of high-temperature superconductivity. In the spirit of the Nobels, it is worth mentioning Bardeen a second time, the only physicist to get a second Nobel Prize in 1972, which he shared with his younger colleague Cooper and student Schrieffer for this, developing the theory of conventional superconductivity. Material science in particular and technological progress in general thrive on good ideas, failed ideas, and serendipity. I hope to have convinced you to revisit your failed ideas and find the hidden potential for success. Thank you.